Welcome back everybody. Let us continue from where we left last time. We were discussing about the adiabatic process. So now what an adiabatic process is? It is a type of process in which the condition PV equals to nRT doesn't hold valid. I'm writing. It does not hold valid. And instead of that, what is valid is PV to the power gamma equals to constant, and from that we will derive various functions. So what is a work done in adiabatic process? So work done would be integration of P dV. Now P into V to the power gamma equals to constant. So we can write P is constant upon V to the power gamma. So it would be integration of constant upon V to the power gamma into dV. Again we take C outside, and now it becomes 1 upon V to the power gamma dot dV. Now it is integration of V to the power minus gamma dot dV, which is equals to integration of this is plus 1, so V to the power 1 minus gamma upon 1 minus gamma. And now we have taken our integration, so I'll remove the integral sign, and now let us put from V1 till V2, and this is now equals to C. I'll also take 1 minus gamma outside. Now it is V2 to the power 1 minus gamma minus V1 to the power 1 minus gamma. Yes. So now let us remove this constant C, and for that we can use, let us first use our equation C V2 1 minus gamma minus C V1 1 minus gamma upon 1 minus gamma. And now how can we eliminate our C? We know C is equals to PV to the power gamma, which can be written as P1 V1 to the power gamma into P2 V2 to the power gamma. So I am writing C as P2 V2 to the power gamma, this substitution over here and this substitution over here. And now we get our equation again as P1, let us substitute P2 V2 into V2 1 minus gamma minus P1 V1 into V1 1 minus gamma upon 1 minus gamma. Now let us write our work done is equals to, now V2 has 1 and there's already a 1, so P to the gamma, and this is also gamma. We actually forgot, I forgot the gamma. So it is PV P2 V2 as the gamma, and the gamma cancels. Oh, here also the gamma and the gamma cancels. Minus P1 V1 upon 1 minus gamma. This is our work done, and we have got it. Yes, this is another important formula. Also keeping into consideration that we do not use our ideal gas equation and we use a simple equation. Now let us derive the bulk modulus for adiabatic. Adiabatic process. We know bulk modulus, that is K, is equals to minus dP upon dV by V. Now we can write dP upon dV as gamma P upon V by V. Now bulk modulus is gamma into P. Now let us understand a bit in more detail about gamma, that is Cp by Cv. We know the formula for Cv, that is Fr by 2. So understanding what is F, that is degree of freedom, it is called as F, and the degree of freedom is different for every different type of gas, and we will see how. So for a monoatomic gas, the degree of freedom is 3, while that for a diatomic gas it is equals to 5. The degree of freedom for triatomic and linear structure is equals to, so triatomic linear, we will visualize it like this. So it can rotate around this axis in one way, it can rotate around this axis, then this axis, so 1 2, then move in all the three directions. So this is 3 plus rotate around this axis in any of in two directions, and along this axis in 2. So this is 2 to 4 5 6 7. So the degree of freedom becomes 7 over here. And for triatomic non-linear, it is, now let us see this gas. We will avoid this and let us take something like a double bond. This is just some an atom. This is also an atom that is not an oxygen. It's like circles that represent an atom. And these are some irregular bonds, and no bond is equal. So let me draw a bond that is long enough. Yes. Now I can rotate it around this axis, and this axis. So it is 3 times R, that is so over here in this axis I can rotate it in 3 ways, 1 2 and 3, and this can be moved in 3 ways, x y and z. Rotate it along this in 3 ways, plus 3 plus 3 plus 3 to the 12. Answer is 9, because we have a formula. Yes, but nobody asks such further, but this is something that need to know kind of thing. Now let us move ahead and understand about the specific heat capacity for adiabatic process, that is equals to 0, as the Q is the change in temperature. Wait, we are writing it for adiabatic process. So over here delta Q is equals to 0. That's why the specific heat capacity is equal to 0. Now let us write it for isochoric, and isochoric process means delta V equal to 0, that is volume is constant. So work done would obviously be equal to 0, and P would be directly proportional to P equals to temperature. So the bulk modulus would be infinity, and specific heat would be equals to Fr by 2, that is equals to Cv. That's it. The next one is isobaric. And in this process, delta P is equal to 0. So V is directly proportional to T in this case, and therefore work done is equals to P V2 minus V1. We can also be written as NR T2 minus T1. Now the slope would be equal to 0 of this graph. The bulk modulus would be 0 and specific heat would be equal to Cp. And now the last two processes are the cyclic process, in which work done is equals to area enclosed by the graph, and in cyclic process all are 0. What are 0? Thermodynamic function terms. I'll write the except work and heat. Yes, you need to remember this by heart. And now the last process, that is an polytropic process, and in this process PV to the power n is equals to constant. Then work done will be equals to, just now we derived, P2 V2 minus P1 V1 upon 1 minus n. And with this we complete the types of processes. We'll meet you in the next episode. Thank you.